Good morning students. Welcome to 11th standard chemistry video class. We are discussing lesson 9 solutions. In our last video class, we completed up to elevation of boiling points. In this video, we will start with the next topic, depression in freezing point. Depression in freezing point. Like boiling point, freezing point also another physical property. Here we are having the definition for freezing point. Freezing point is defined as the temperature at which the solid and the liquid states of the substance have the same vapor pressure. At freezing point, the solid and liquid phases of the substance are in equilibrium. For example, the freezing point of water is 0 degree Celsius. At this temperature, the ice and water are in equilibrium. Consider a non-volatile solute which is added to water at its freezing point. It forms a solution, where the freezing point of the solution is lowered from 0 degree Celsius. The lowering of the freezing point of the solvent when a solute is added is called depression in freezing point. It is given by delta Tf. From this graph, we infer that the freezing point, that is T0F, is 0 degree Celsius as the vapor pressure at this temperature is 1 atmospheric pressure. The vapor pressure versus temperature curve for the solution indicates that the freezing point Tf is lower than 0 degree Celsius. The depression in freezing temperature delta Tf can be expressed as delta Tf equal to T0F minus Tf. The experimental results shows that the depression in freezing point is directly proportional to the molar concentration of the solute particles. Hence, delta Tf is directly proportional to m. It can be also written as delta Tf is equal to Kf into m. It is given by equation 9.30. Here, m is the molality of the solution, where Kf is molar freezing point depression constant or cryoscopic constant. If m equal to 1, then delta Tf is equal to Kf. The Kf is equal to the depression in freezing point for 1 molar solution. Next, let me discuss determination of molar mass of solute from depression in freezing point. Consider a solution which is prepared by dissolving Wb gram of solute in Wa gram of solvent. Then depression in freezing point is given by the following equation. Delta Tf is equal to Kf into Wb into 1000 divided by Mb into Wa. It is given by equation 9.31. Here we have to calculate molar mass of solute. After rearranging equation 9.31, we will get Mb equal to Kf into Wb into 1000 divided by delta Tf into Wa. It is given by equation 9.32. This tabular column gives molar freezing point depression constant for some solvents. Hence, we completed depression in freezing point and determination of molar mass of solute from depression in freezing point. Next, let me discuss osmosis and osmotic pressure. Osmosis and osmotic pressure. First, we will discuss osmosis. What is osmosis? Osmosis is a spontaneous process by which the solvent molecules pass through the semi-permeable membrane from a solution of lower concentration to a solution of higher concentration. The name osmosis is derived from the Greek word osmos, which means to push. It is also important to know that the semi-permeable membrane selectively allows certain molecules in the solution to pass through it but not others. It is explained with an example. Consider a chamber which contains two compartments, which is separated by a semi-permeable membrane. The first compartment is added with water, that is pure solvent. Aqueous sodium chloride solution is added to the second compartment. Hence, the liquid levels on both the sides are equal. Hence, there should be difference in concentration between the liquids present in the two compartments. Since the water molecules move from first compartment to second compartment through the semi-permeable membrane. Here, the semi-permeable membrane allows only the water molecules to pass through it in either direction but not sodium chloride. Now, water flows into the sodium chloride solution. Hence, there should be increase in volume. Due to the addition of water, the concentration of sodium chloride solution decreases and it creates the pressure difference between the compartments. This pressure difference pushes some of the water molecules back to the solvent side through the semi-permeable membrane until the equilibrium is established. At the equilibrium, the rate of movement of solvent molecules on both the direction are equal. The pressure difference at the equilibrium is called osmotic pressure. It is denoted by pi. Thus, osmotic pressure can be defined as the pressure that must be applied to the solution to stop the influx of the solvent, that is, to stop osmosis through the semi-permeable membrane. Van found out that for dilute solution, the osmotic pressure is directly proportional to the molar concentration of the solute and the temperature of the solution. He gave an equation to calculate osmotic pressure, which is now called as Van equation. It is given by pi equal to C or T. It is given by equation 9.31. Here, C is the concentration of the solution in molarity, where T is the temperature, where R is the gas constant. Now, we will discuss the determination of molar mass from osmotic pressure. According to Van equation, pi equal to C or T, where C is equal to N by V. Here, N equal to number of moles of solute dissolved in V liter of the solution. Therefore, pi equal to N divided by V into RT. The above equation is rearranged into pi into V, which is equal to N into R into T. It is given by equation 9.33. If the solution is prepared by dissolving Wb gram of non-volatile solute in Wa gram of solvent, then the number of moles of solute N is given by N equal to Wb divided by Mb. Here Mb is molar mass of the solute. Substituting the N value in equation 9.33, we will get pi equal to Wb into RT divided by V into Mb. After rearranging the above equation, we will get Mb equal to Wb into RT divided by V into pi. It is given by equation 9.34. From this equation 9.34, we can calculate molar mass of solute. Next, let me discuss significance of osmotic pressure over other colligative properties. Unlike elevation of boiling point for 1 mole solution and depression in freezing point for 1 molar solution, the magnitude of osmotic pressure is large. The osmotic pressure can be measured at room temperature, enables to determine the molecular mass of biomolecules which are unstable at high temperature. Even for very dilute solution, the osmotic pressure is large. Next, we will discuss isotonic solution. What are isotonic solution? The two solutions having same osmotic pressure at a given temperature are called isotonic solution. When such solutions are separated by a semi-permeable membrane, solvent flow between one to the other on either direction is same. That is, the net solvent flow between the two isotonic solutions is 0. Here we are having two more solutions, namely hypotonic and hypertonic. If the solutions are too dilute, then it is said to be hypotonic. If the solution is too concentrated, then it is said to be hypertonic. The osmotic pressure of the blood cells is approximately equal to 7 atmosphere at 37 degrees Celsius. The intravenous injections should have the same osmotic pressure as that of the blood. If the intravenous solutions are too dilute, that is hypotonic solution. Here, the solvent from the outside of the cells will flow into the cell to normalize the osmotic pressure, and this process, which is called hemolysis, which causes the cells to burst. On the other hand, if the solution is too concentrated, that is called hypertonic solution. The solvent molecule will flow out of the cells, which causes the cells to shrink and die. For this reason, the intravenous fluids are prepared such they are isotonic to blood, that is 0.9% mass by volume sodium chloride solution. Hence, we completed the topic osmosis and osmotic pressure, and also we completed the lesson solutions. Thank you.